Hi everyone, my name is Varun Chandrasekhar, and today I'll be presenting an introduction to my research titled The Classification of EMG Signals Using Machine Learning for the Construction of a Sound-Speech Interface. With upwards of 7.5 million people in the United States alone suffering from speech impediment conditions such as stroke, ALS, or cerebral palsy, many people rely on speech and communication aids. Traditional speech interfaces, which I will refer to as conventional speech interfaces or CSIs, either rely on invasive strategies, cumbersome setups, or on physical and face movements, which reduces their usability and accuracy in everyday life. These systems make the user perform specific muscle movements to select letters or words that the user wants to communicate. CSIs proved to be an extremely slow and fatiguing speech aid. Newer and more efficient CSIs stipulate the use of sound speech technology. So what is sound speech? Sound speech refers to the act of minimally or internally articulating words without producing sounds. Producing sound speech is analogous to talking silently without moving the mouth. This is far less fatiguing for patients than attempting to speak by projecting their voice. Sound speech can help develop a speech interface as it engages speech muscles in a subtle manner, creating electromyograph signals, which are electrical currents generated by muscle contractions, which are shown here. Sound speech produces EMG signals in certain patterns. So when the same words are spoken, the same muscle contractions occur, and correspondingly the same specific EMG signal patterns are generated. So assuming that the EMG signals are produced by sound speech can be recorded, it's possible to identify the pattern of the signal to determine what was spoken. EMG signals used in these speech interfaces are conventionally collected from the surface of the skin and are thus known as SEMG signals. These new speech aids, known as sound speech interfaces or SSIs, measure downstream signals from the speaker's speech system, and when an internal speech muscle is neurologically or volitionally engaged through sound speech, sensors are used to pick up the electrical EMG signals generated, and computer algorithms are used to translate these signals into language. Machine learning technology is used with SSIs to identify and isolate patterns in the EMG signals and classify them into the speech produced. In other words, ML algorithms translates EMG signals, and other certain algorithms likely translate EMG signals more effectively and accurately. The two types of ML models that will be evaluated in this study are the convolutional neural network, also known as a CNN, and various pattern recognition algorithms. In a CNN, images are passed through a variety of layers that learn features of an image, and through several other layers that classify the image into one of several outputs. Pattern recognition algorithms attempt to develop a division, as seen here, between multiple classes shown in red and blue. These algorithms were explored due to the gap in research present on the optimal ML model to use in a sound speech interface. Studies on SSI, such as Arnav Kapoor's research, which is one of the most advanced research on the development of a sound-speech interface, makes use of a convolutional neural network, whereas Schultz's studies makes use of a type of pattern recognition to classify EMG signals. These studies, along with others, do not justify the use of the ML model for classification, and instead choose one based on convenience or ease of implementation. This leaves a major gap in research, as no study has been explicitly found to determine the optimal machine learning model for use in a sound speech interface. A research study by Karlik and colleagues trained and compared various machine learning models, finding that the CNN yielded the highest EMG classification accuracy. Although his study identifies the optimal machine learning model for classifying EMG signals for arm prosthesis, it still doesn't identify the optimal machine learning model to classify SEMG signals for use in sound speech interfaces. This is an important distinction, as SEMG signals collected from muscles in the speech system have more subtle patterns due to the weaker signals produced and the variations in regular speech as seen here. Because of this distinction between the signals generated from the speech system and the arm, there's still a lack of understanding the optimal ML model to use for SEMG classification. This led me to ask the research question, which type of machine learning algorithm, a convolutional neural network or pattern recognition, is most accurate at classifying surface electromyograph signals from the submental triangle, which is the area under the chin, to develop a non-invasive sound speech interface? In parallel to this research, I had also developed an engineering goal to develop a non-invasive sound speech interface with greater than 80% accuracy. I had two main assumptions going into this research. One was that it was possible to obtain accurate EMG data from low-cost muscle sensors as shown here, and two, that the Arduino would have a high enough sample rate to generate detailed data for machine learning models. The main significance of the study is that it will improve the accuracy and speed of communication aids for those with speech impediments. To perform this research, a device had to be created which attaches to the speech system using electrodes, and then EMG recordings must be generated using the device. The EMG data will be generated as a series of comma delimited values from 0 to 1023, and after the data has been collected, a machine learning model can be developed to classify the EMG signals as shown here. And the accuracy values of the model will be calculated to compare the effectiveness of each ML model. This method is a standard process used to test ML algorithms in several other studies such as Kapoor's and Schultz's. While doing this research project, each ML model will have to be trained and tested on the same data to ensure validity of results. Other than that, there are no ethical or safety concerns involved with this project. And that concludes the introduction for this research project. Thank you for listening.